Hi, and welcome to the final project presentation presented by Curtis Goodwin for AUTA 5900 Special Problems Deep Learning. Quick overview of the presentation. I'm going to go through the project objectives. I'm going to go through a description and quick EDA of the data, discuss a simple RNN model to predict sine wave function. I'm going to talk about the LSTM cell structure and the gates and how they function. I'm going to talk about stock trend prediction, particularly Sabre stock with LSTM network model. We're going to walk through the redesigned stock trend prediction with another LSTM network model. We're going to compare the results of the two models and then a quick conclusion and thoughts for further consideration. The time series data that I collected, I scraped from Yahoo Finance using an API in Python called Yahoo Fin. I scraped all relevant information for Sabre stock over the past 5 years. It included 7 features, 1,467 observations. Of the data types for each feature, one was a string that included the ticker number or the ticker label for Sabre. It included 5 numeric variables and then 1 date time variable for each day that was recorded. The variable that was integrated in the LSTM model later in the project was just the Sabre raw close price, but we'll do a quick EDA of all 7 variables. So I provided a snippet of code that allowed for everybody to observe where the data was scraped from. And the API, you put in the ticker, the start date, and the end date. So the large data set, which was 1,467 records, was used for the training set, and then we wanted to forecast 33 days that resembled what happened to the stock market when COVID-19 hit. Also, the first 5 records of the data frame are observed. Some initial visuals to go along with our EDA. I provided a line chart for the open, the low, and the high. Although they represent different values per day, you can see that the trend lines are correlated and trend in the same position. Here I calculated box plots and histograms for each subvariable that was numeric in the data set. The one interesting fact was how the adjusted close was, the central tendency was higher than the raw close price. And so that could be accounted for dividends being added in and other features that go into the adjusted close. And then that was also represented in the distribution of data with the histogram to the right. And you can see that the adjusted close was skewed. Volume displayed several outliers above the interquartile range, and that's evident in the long right tail here. The other numeric variables appear to be relatively normally distributed. So to conclude the visual part of the EDA for the dataset collected, there's a scatter matrix that showed linear correlation between all numeric variables, and as expected, all but one were demonstrated strong linear correlation, and this is because whether there was positive change or negative change per day, the high, the low, the close, the adjusted close would all follow the same trend line per day over the last 5 years. The only one that differed in relation to the close price was volume, and you can see some outliers there, not much of a linear correlation. While we'll come back to the dataset that was scraped from Yahoo Finance later when we implement our LSTM model, first we're going to construct a sine wave simple RNN model and then observe its predictive ability and then compare that with the LSTM model. So for the sine wave, we contrived our data set through using the linspace function in Python. The parameters were 0 to 60 and the domain split up into 800 even intervals, and then these were set to input lengths of 60 sequence data points. The batch size was set to 32 samples, meaning that we're taking 32 samples per batch of length 60 data points per sample. The model construction can be viewed on this slide. We used one feature to train the model. The model was sequential. we used a simple RNN with 65 neurons. The input shape was made up of the length and then the features. And then we had one fully connected layer using dense, and that gave one output layer. The optimizer used was Atom, and then the loss or the cost function that we minimized on was the mean squared error of the predicted values. Next, we're going to talk about a little bit more of the design for the simple RNN model. Here you can see the parameters where we have 8 data points split evenly between domains 0 to 60. And we have our input layer x1 through xn. And it's going to be fed through our activation function, our simple RNN. And then this activation function is going to adjust weights in our hidden layer. And then this is where the memory is stored. So as we adjust the weights by optimizing on the mean squared error, what's going to happen is that memory, that stored memory from recent input, is going to be fed back through a recurrent loop, and it's going to be stored and then processed and applied to the next sequence that's passed through the activation function. The recurrent network that's the feedback loop and acts as stored memory is known as backpropagation. And backpropagation uses the gradient-based optimizer, which is Atom, where we adjust the weights based on minimizing the cost function or the loss in the mean squared error, and we apply it to the next sequence. The next sequence would be known as the batch. So remember, we have a batch of 32 samples with length 0 to 60 data points that are being fed through, and this is how we're training our model. And through all of those, we're going through one learning cycle, which is an epoch. The number of epochs used in this model to train the sine wave function was 15, and so as each epoch is trained, or one learning cycle is gone through and trained in the model, a certain amount of loss is calculated and then reduced for the next epoch. And at the end, we have our fully connected feed-forward layer that gives us an output layer prediction. Following all the training cycles or epochs that were run through the model, we can see the model summary, which gives us the number of neurons used, the shape of which we inputted our data, and then the feed forward or the dense network that gave us our output, and then how many total parameters were trained on. This slide shows the amount of loss over the number of epochs used, where the training error loss was reduced and then predictions were processed at the end. So we can see that for the first epoch, the first training cycle, we had a lot of loss. And then steeply through our stored memory, we dropped that loss and reduced it. And then at times it would peak, and then we would learn from it and we would reduce it. And in the simple RNN, there's times where we have to learn later in the epoch, but eventually it does level out. And as you can see, as we move towards the end behavior starts to flatten out how much loss or how much error we've reduced. And at that point, now we want to go ahead and make a prediction for the simple RNN sine wave model. So here's our visualized prediction. We can see that the prediction, which is in orange, compared to the actual sine wave, which is in blue, the prediction was slightly overcompensated at the curvature and the turns where there is local mins and local maxes. And so part of this is we overestimated at the maxes, we underestimated at the minimums, but we can see that it does change concavity around the same time that the actual sine wave changes concavity for each turn and each curve, which is pretty unique over the domain 0 to 60. So now let's talk about the LSTM cell state and how this can maybe improve from the simple RNN or the vanilla RNN model in terms of getting those predictions a little bit more accurate to the actual values. So what is LSTM? It stands for long short-term memory. It's more robust than the simple RNN, it utilizes a gate structure which allows us to retain or forget information over a long period of time. And that's really important because a simple RNN only learns what is most recently processed. And so the simple RNN has good short-term memory, but exponentially loses its long-term memory, whereas there's some structures in place of the LSTM that allow us to retain information over long periods of time. The LSTM possesses a cell state which acts as its own individual neural network, and there are 3 gates in each cell state. Each gate possesses a sigmoid activation function, and that sigmoid activation function kind of defines why we call it a gate. It allows information in, or it doesn't allow information in. And so basically, it's the gatekeeper of what is relevant information and what are we going to keep. The cell state also has a TANH activation function that processes the data. So if the sigmoid determines that the data is relevant, then we process it through an activation function. And each cell state can be compared to a hidden state of a simple RNN with one major difference. The simple RNN does not have the gate feature. The gate feature allows information, relevant information, to be retained from one cell state to the next until it's determined not to be relevant anymore. So the gate function really keeps our long-term memory of what the model determines is relevant information, whereas the hidden state feeds back stored memory to the next batch sequence coming in, but it's updated and we lose some of that stored memory. That's why the simple RNN only has short-term memory, whereas because of the gate, we have short-term and long-term retention in the LSTM cell state. Below is a quick model or diagram of what one cell state for the LSTM looks like. So we have some input that comes in, and then we have 2 sigmoid functions. One sigmoid function is the activation function if the information is deemed non-relevant. We call this the forget function. And so this information is actually discarded. And then we have the information that is deemed relevant, and it's processed through our next activation function, the TANH. And so the relevant is passed through and it's kept. And then what happens is as it comes out the TANH, it's processed through another sigmoid function, and that determines if it's still relevant, and then we can either keep it or we can lose it. The cell state for LSTM can be viewed in 2 different perspectives. One is flow in a channel, and one is a cell state in a snapshot. A great illustration is thinking of cars driving on a highway. If we're looking at flow in the channel, we're looking from a holistic point of view where we want to see what type of information is being retained, and that would be similar to looking at the traffic flow. So we're not looking at one specific piece of information, but all the information as it flows through the channel, some exiting, some entering into the channel, similar to a highway where cars exit and enter, but we're not looking at one specific car. The snapshot is going to freeze for a moment in time, and we'll be able to see what information is on the highway and what information is not on the highway, where our spots kind of bare, and where maybe we have a log jam of information. And so this is one moment in time. That's why we call it a snapshot compared to the flow of the overall information traffic through the channel. To apply our LSTM cell state into an actual LSTM model, we're going to use the historical data that was scraped from Yahoo Finance, the Sabre stock close prices, and now we're going to give our model some parameters and start building the model and kind of see the results in comparison to maybe the sine wave and see how the LSTM model can improve upon the simple RNN. So in our initial model, the parameters we kept were 60 data points. That was our length. Our train test split was 90% train, 10% test. The length of the normalized training data, so after we normalized it, how much data did we have, was 1178. Our batch size was 32 samples. The model design We had 3 LSTM layers with 2 dropout layers after each LSTM layer, and then we had a final feed forward layer that used the dense function.